Okay, so we said the width of a moment is, those are our delta x intervals. So the width of the moment in this particular case is 1.5. 1.5, and that's delta x. Okay. What are all possible values of dx? From what to what? The change in x could be 0 up to 1.5. It's dx is the change in the current interval, so that starts at 0 and ends at 1.5. So that would be answer, was it in D? D, answer D is correct. Okay, next question. What is the value of dx when the current value of x is 6? So if we pause at 6, right there, the current value of x is 6. We should be able to, let's do that. There's the current value of x. We've paused life here in this animation. We've paused life, and the current value of x is 6, and it's asking for the value of dx. What is it? 1. 1. It's 1 because it's from left x to the current value of x is 1. And enter the number of completed intervals. So now, again, the current value of x is 6. How many completed intervals? 3 completed intervals. 6, the current value of 6 is in the 4th interval, so 3 have been completed. One more question. What is the current interval? What is the current interval if the current value of x is 6? From what to what? 5 to 6.5. The current interval starts at 5, ends at 6.5. One more. The last one is, what is left x if the current value of x is 6? 5. Right now, it's showing the current value. So it's what? The x value at the left side of the current interval. All right, questions. So I think we went through them all. Okay, let's close them up. Next. Okay, so from all this stuff was our building blocks for the approximate accumulation function. Right? So this all was involved in building the approximate rate function. All this stuff we just talked about. From the approximate rate function, we built the approximate accumulation function. And we talked about this on Thursday. So what I want to do is I want to relate. So what is this showing? This is showing how the approximate accumulation is built as x increases. Right now I'm showing delta x of 0.4. I think for our handout we had delta x of 0.3. But here's delta x of 0.4. And it's showing as the constant rate function, the approximate rate function emerges, how the accumulation function emerges with it. Okay, that's what this is showing. So I'm gonna highlight some values and things on this one at a time, and you want to relate what I'm doing to our approximate accumulation function. So now we're talking about the approximate accumulation function. So here's the first thing. So the question marks. The question marks are showing, they're displaying some value related to something involved in the approximate accumulation function. Take a minute to decide, like what would you put a circle around that you would say, this is what those question marks are equal? What would you put a circle around in the equation to say, this is what those question marks are showing, the value that they're showing relative to that function? Talk, go. Okay, where's Madison? Halverson? Madison. Right here. How'd you do? So each question mark represents what? Each question mark represents what? Okay, she's saying in relation, first of all, she's saying that those question marks relate to the completed intervals. Would you agree with that? Okay, so what does one question mark then represent relative to the completed intervals? One question mark, one of those. Want to try it, or should I? What would one question mark mean? Where is Manuel Perez? Yeah. And the change. The change in the quantity for one completed interval. He wants each question mark to be the change in the quantity for one completed interval. Agree or disagree? Yes or no? Yes. Yes. Each one of those question marks is showing how much the weight increased due to one completed interval. Due to one completed interval. So what would you circle? What would you circle to represent what one question mark is showing in here? What would you circle? Where is it Navit? Navit. Kur. What would you circle in the A function to represent the accumulation due to one completed interval or one question mark? The left side of the plus sign. So this whole thing? Okay, she wants this whole thing, the summation of that. So what would be different? Without the summation sign. So it was close. So it was close. What we want, one question mark is this. What he said, dy, or a little bit of accumulation due to one interval. So then, last we had questions about what do the j values mean? So how does the j work? So the way j works is, first, j equals 1, and it's 1. And what happens? When j equals 1, it computes the amount of accumulation for the first completed interval. And what is that? That amount right there. So when j equals 1, you get that amount of accumulation from that first question mark. Once that's done, then j becomes 2. J changes to 2. And what does it do? It calculates the accumulation for j equals 2. When j equals 2, it puts j equals 2 through this ringer right here, and that comes up with an amount of accumulation due to the second interval, j equals 2. And that's this. And then j turns into 3. So what happens with these summations is you go one at a time, j equals 1, and you calculate that product. And then j becomes 2, and you calculate that product, a little change in weight. And then j becomes 3, and then you calculate that product. And then the summation does what? Adds all those up. So it takes them one at a time. J equals 1 finds the amount of change. J equals 2 finds the amount of change. J equals 3 finds the amount of change until what? Until this is the number of completed intervals, right? And so until the last completed interval. So this is just j starts at 1 and ends here. So it ends with, right now, what is it? Right now, this value of this right here is 5. The last completed interval is the 5th. So right now, where I've paused it for the current value of x, we've made it through 1, 2, 3, 4, 5 completed intervals, so that floor function equals 5. So j is going to be 1, then j is going to be 2, then j is going to be 3, then j is going to be 4, and then j is going to be 5. For each one of those, it's going to compute a little bit of accumulation, and then it's going to add them all up to get the total accumulation for the completed intervals. Did you have a question? Yeah.
Yeah, so you were saying the question marks are without the summation.
That's right.
But j equals 2 is only as high as it is because it's added on top of j equals 4, right?
It's j equals 2 is this quantity right here, which starts here and ends here.
But it starts at the bottom because it's already added
Right. J equals 1 gives an amount of accumulation, and now J equals 2 picks up from there.
Right. So that shouldn't be summation too? Shouldn't summation be involved with that as well?
No, because I was asking, what does each individual question mark, what would you circle to mean each individual question mark?
Right, but if I'm looking at question mark 2, I would assume that's J1 and J2.
No. J2 is just the amount of accumulation starting from here and ending from here, and that's this when J equals 2. Doesn't include J equals 1. It doesn't include J equals 1. You haven't added on. Okay, let's keep going. Is that help? Is that better?
Well, I feel like the second one is added to the initial of the first one.
It is added on, but not if J is 2. We're just talking about what you get when J equals 2. And that is this amount right here. If you plug J equals 2 into this, that value is this amount of change. It's this dy.
Okay, that makes sense.
Is it better? It's not till we get them all. We get the J equals 1, and so here, let's do the next thing, and I think that'll help.
No, I get it.
Good, excellent. Here we go. Moving on. I think this addresses your question. This should address your question. Okay, so I'm representing the coordinates of that point in 2 different ways. As an ordered pair, and then as distances on the axis. So it's kind of repetitive. The coordinates of this point right here are the same as what? This is the x coordinate, and this is the y coordinate. What do they represent? Go, talk. Okay, where's Keen Miller? Where's Keen? Is Keen here? Oh, there you are. Okay. So let's talk about the x-coordinate first. So the x-coordinate that I'm showing here at any given moment, at any given current value of x. So let me just pause it here. Pause. What is that x value? The x value. Keen. Okay. How about Christiana again? What is the x, the x coordinate, that question mark that would be the x coordinate? How would you talk about that or represent that or relate it to our a function? It has a name, or it has a way of getting it. Volunteer. What does it? Yeah. He wants left x. Is it the left side of the current interval? Yeah, that's what it is. It's also what? The right side of the last completed interval. So that x coordinate is what? It's the x value starting at the current interval. Okay? All right. What about the y coordinate? That's really what this is about. This one is really about the y coordinate. What does that y coordinate represent? Where is it Quinn? Marble?
Yeah, right here.
Tell me. So what about the y coordinate?
Like in words or mathematically?
Either.
Well, it represents the accumulation of weight at left x.
Okay. So how about relating it back up to the?
To the equation.
Yeah.
It would be what interval
Yeah, this is always, it's always locking on to the beginning of a moment, okay? Or the end of a last moment. So,
Okay, so you just plug 5 in for J if it's the 5th interval.
and then what part of the equation would calculate that y coordinate? Is it this stuff over here or this stuff over here? A or B? Yeah, what about this part? Is that y coordinate? How about Sierra Cats? Sierra, how do you relate this y coordinate of this point here to what's going on over here? Not sure. Volunteer. Yeah.
That part is just
The whole thing? He wants the whole thing. The whole thing equals this y coordinate represented by this question mark. The sum of all the little accumulations for the completed intervals. That's it. You got it. So this is now, do you see it? Yeah. Yeah. So now we're summing them all up. So that would be with the summation. It would be the sum of all of the accumulation from the completed intervals. And then because we're at the end of the last completed interval, that's the same x value as the beginning of the current interval. So left x doesn't really deal with the completed intervals, but just because it's the end of the last completed interval, it's the same as the start of the current interval. Does this make sense? Okay, next one. Okay, what do they mean? And symbolically, how do we represent them? What does it mean? And symbolically, how do we represent them? Go. Okay, where's Mashbir? Hussein. Mashbir. How about this question mark here that's showing the horizontal segment? What is that? Can you say what that is representing the horizontal segment? Okay. Is it relate to the completed intervals or the current interval? Relates to the current interval. And so what is that in the current interval? dx. That's dx. That's the change of x in the current interval. dx. That's that question mark. Okay? What about and so where do we see that in the whole equation? Where do we see that? Where do we see dx in the whole equation? Where is Joshua Gonzalez again? He's not here again. How about Nicholas Avalos? Nicholas, where in the equation do we see dx?
It's the r left x, x minus left x.
He wants this whole thing. That's where we see dx. Agree or disagree? Okay, if it's not the whole thing, then it is dx is this. How far we've gone into the current interval. Final minus initial. Final minus initial. That's dx. So that would be the question mark representing the horizontal change. Okay? Vertical change. How about Darren Sims? Is Darren here? Darren, how about that vertical change for the question mark? What is that? You think it's the whole thing? And what is that whole thing? What is that whole thing? What is it? The what's that? Which dy is it? Right, the dy for what? He wants dy for the current interval, or the change in weight in the current interval, and he wants the whole right expression. That's it. Good. That's it. Dy is m dx, right? So it's the constant rate times the change in x for the current interval. So that's this question mark here. Let's just pause it. Oh, jeez. There we go. So that whole thing is calculating then the change in weight due to the current interval. Due to the current interval. Okay, last one. You guys are doing good. Go. Hopefully this one's easy. Hopefully this one's easy. Where's Coles, Weber? Coles. Coles, Weber. Is that Weber last? You're not Weber. Okay, not here. Hector. Bottom question mark. He wants X. What do you think? That's the current value of X. You got it. That's the current value of X. Okay, where do we see that? Everywhere we see an X. That's the independent variable of this function. It's the current value of X. That's the independent variable. And then there's, it's over here. It's here. It's in our, to get our, how many completed intervals? It's here, and it's here, and it's here. Okay? What about the other question mark? Vertical distance there. Where's Angela? Yeah. Angela. Yep. What's that? The whole thing, and what does the whole thing mean? So she wants the whole thing, and I agree. And how would you? What would you say? What would you say? What is that, Angela? Okay, accumulation not of intervals, but accumulation of what? What quantity? What's that? No, X is our time quantity. So it's accumulation of, where's Laura? De La Cerda. Accumulation of what? Where's Laura? Okay. This is the accumulation of what quantity in this situation? What's that? Yeah, and what is Y in this? What is the real world quantity?
100 pounds per second.
Per second?
I mean, total weight, sorry.
Total accumulation of weight. Due to completed intervals and the current interval. For the current value of X, we have the completed intervals plus the accumulation of weight due to the current interval. So this is the total accumulation of weight at X seconds in hundreds of pounds. And it's the whole sum. It's the dependent variable of the function. Okay, I hope that helped to really understand that, how that thing is working, and then relating it to the graph. All super important. Okay, now this is the moment we've been waiting for, because we've made it 3/4 of the way through the progress of this journey that we wanted, right? We know how fast the quantity is changing at every moment. We want to know exactly how much we have at every moment. Not approximately, exactly. Okay? So this is going to be kind of fast. It's going to be kind of fast. So here's back to delta x of 0.3. So talking about getting an exact accumulation function means first talking about getting a better approximate accumulation function. How can I make the approximate accumulation function better than this one? And probably everyone knows that. You should all know that. What do we do to get a better approximate accumulation function? Smaller intervals will make a... So I'll do a smaller intervals here. Here's now delta x equals 0.1761. So what happens to the approximate rate function? It becomes better, right? It becomes, with the smaller intervals, you see now that those steps are doing a better job trying to pretend to be the exact rate function. And then what happens? As a result of a better approximate rate function, now we get a better approximate accumulation function for smaller intervals. Let's make them smaller again. Here is delta x of 0.076. Notice the step function, the approximate rate function, staying much closer to the approximate rate function, and so we expect a better approximate accumulation function. And so then what do we want? We want super small intervals. So small that we can't really tell the difference between the approximate rate and the exact rate. So do you see how it's basically the curve now. This approximate rate function is basically the original curve that we had. But is it? If I zoom in, look what happens if I zoom in. What do you see? There's still constant rates approximating that original rate function. Okay? But it's so small now, this is 0.005 seconds, delta x. Those moments, those delta x intervals are so small that we've essentially recreated the exact rate function with constant rates, and the resulting approximate accumulation function we get is, I'm going to turn on the exact accumulation function. And there's no daylight between them. Do you see that? So now they're both on. So both the approximate accumulation function and the exact accumulation function are on. So the approximate accumulation function we get when we use super small intervals is essentially the exact rate function. And if we can't distinguish it, if it's like, splitting hairs to such a degree that essentially they're the same. Okay? So that's the last piece of the puzzle. You take your approximate accumulation function and you make your intervals smaller, and then you make them small enough. What is small enough? Small enough so that you can't tell the difference between the approximate accumulation and the exact accumulation, and then we have it. Then we have it, the exact accumulation function, or we know exactly how much we have at every moment. Okay? So now what's the notation for that? You did some of that in your homework. So now, just to let you know, I've changed the W to F, right? So what was W before is now F. Hope that should be okay. And so here's the progression of things. Which function comes first? Exact rate of change. You know how much a quantity is changing at every moment. You want to know exact accumulation, how much you have at every moment. So we know that we first build the approximate rate function, and then we build the approximate accumulation function, and then we make the interval small, and we've got the exact accumulation function. So here's the approximate accumulation function that we built. And so when the intervals are really, really small, we don't write this anymore. When the intervals are really, really small, so that we essentially have the exact accumulation function, we write this instead. Okay? This is the same as what's exactly above for really, really small intervals. Small enough intervals, okay? So these two are the same. So this is same as for small enough intervals. Okay, so where in this new notation do you see the similarities to the old? So let's break it down. What about this new notation is expressing the same thing as our approximate accumulation function above, just in a more compact version? So what is one thing you see that's similar about this new expression here, which is called an integral to our approximate accumulation function? Volunteer. What's one thing you see that's the same? Yes, ma'am. Summation sign. And now in the integral we have what? So we're summing up what? A bunch of little amounts of accumulation. And we're doing that here too. We have a different symbol. So this is Greek sigma, and this is German S. So they're both like S's for sum. The sigma meaning chunk, one chunk at a time. One chunk at a time. The German S now, the intervals are so small that it's like a continual addition of these itty-bitty amounts of accumulation. So it's more continuous addition, right? But it's still sum. So we still have the German S. German S still means sum, just like the Greek sigma did. Okay, what else? All right, what else is the same about this new expression that you see related to what's above? What else do you see? Yeah.
I see a change in accumulation.
And where do you see? Good. Where do you see the change in? Good. She's looking at this right here. This is crucial. This is crucial. Do you recognize that? What is that? Who's up? Montarius, Howell. Montarius. Where's Montarius? All right, Montarius. Do you recognize what I put a red box around? What is that?
It's the same. Everything to the right of the sigma, but to the left of the plus sign.
Okay, so you're seeing it's kind of like this? All right, so it's rate times a change in x. Rate times change in x. It's just now that there's no, the intervals are so small that there's no changing dt through the intervals anymore. It's just there's small intervals, that x is just increasing through the intervals, and we're adding up all these changes of the current rate times the little change, current rate times little change, and it's like we don't, the intervals are so small that there's like no difference between delta x and dx anymore. And so just x is continually increasing, and we're just rapid fire adding up all these little changes. Rate times change, rate times change, rate times change, where the change is very, very small. So we don't need to break it up anymore. There's no completed and current. It's just all these tiny intervals sweeping out, and we're adding up all the accumulation bit by bit. Rate times dx, rate times dx. Okay? And then the A means what again? Where we start accumulating, right? So that was here. We saw that here and here. Where we start accumulating up until the current value of x. The current value of x. So this expression, this notation, is really embodying everything we had up there, but just in a more compact way because our intervals are so small. We don't need to distinguish completed from current interval anymore. And we just add up all these bitty changes. Just continually adding up bitty changes as x increases. Okay, so the question arises, why inside here do we have t's? Well, so read it meaningfully here. Okay, so read this meaningfully as a sub f of x is the accumulation of changes in f due to changing at the rate of r sub f of t at every moment from a to x. Okay? So it's the accumulation of changes in f, we'll talk about f in a second, due to its changing at the rate, our exact rate, at every moment from a to x. Okay, so why do we need this new variable t when it just should be x? Shouldn't it just be x? It should be from a to x, r sub f x dx. I mean, that's really just the x value. We'll tackle that Thursday. We got to get to something else today. So we'll just put that question on hold. So that if you were wondering why do we just bring t into it and x, good, all right? Good that you were wondering that, and we'll tackle that Thursday. So now what about f? So this is the accumulation of the quantity. What about, we talked about amount functions. So suppose that the scale already had p 100 pounds of sand on it. Now the function f. All along we talked about this. We're talking about some function f, right? What is f? F is the total amount of sand of weight on the scale. So can you write the function f? So if p already had if the scale already had p 100 pounds of sand on it, could you write the function f? So f of x equals what? Which would be the total weight on the scale at the current value of x. See if you can do it. Do it with someone next to you. What's that? Yeah, but that's all on video, so. Okay, where is Emily? Forgate. Emily, how'd you do? Tell me what do you think the function f is? So what, did you come up with the function f? What do you think it might be? How would we do? So.
We thought you were asking like what a and f was and what a was.
Oh, sorry. So what I was asking was, if the scale already had p 100 pounds of sand on it, we want to come up with now the exact amount function. What would the exact amount function? Can you do it on the fly, or do you want to pass to someone else? Could you come up with what would the exact amount? So what total amount of weight on the scale at any value x? Yeah, you want to try? Total amount now at any, so if this is the accumulated amount at x, right? And where does that start? Where does the accumulated amount start? 0. When x is 0, there's no accumulation, right? Even though there's p pounds on the scale. So what would the function f be? Yes. All right, so she wants p plus all this. Did you say that back there? Okay. You said it, but you didn't say it out loud. That's okay. Yeah, I know. So, difference between an accumulation function. Accumulation always starts at a value of 0. The accumulated amount of the sand, even though there's sand starting on the scale, if we're doing an accumulation function, that starts at 0. It's the new amount, the changes adding up. So for the amount function then, it would be whatever initial amount you had plus the accumulated amount. So that f function that we were talking about from the beginning. So look, that was this f function that we talked about from the very beginning. The rate of change of the exact amount. The rate of change of the exact amount. That exact amount then would be p plus the accumulated amount. Exact accumulated amount. Anybody have a question about that? Are we good? Okay, so we have a little time to work on an important example. Can we go on? Oh, there it is. Okay, there's the pretty version. Okay, there's the pretty version. Question, yeah.
How would you say
Okay, hold on.
how would you express that? Just saying what it is.
That's the exact amount of sand on the scale at the current value of x.
No, but I mean like part of integral. How would you
Okay, good. So how do we say this? This is the integral from a to x. This is the integral from a to x of r sub ft dt. The integral of a to x of r sub ft dt. Yeah, thanks. That's a good question. Other questions? Okay, example. Here we go. A tub has a clogged drain. It still lets some water through. At t equals 0 minutes, the faucet is turned on. So the faucet's on and it's also leaking. It's also draining, kind of. Right? So those are both happening at the same time. Okay? The following graph shows the rate of change of volume of water in the tub in gallons per minute as a function of the time in minutes. Can we get through these 5 questions before the end of class? See if we can do it. D and E are the most important. No, they're all important. They're all important. Go. If you haven't gotten to D and E yet, go right to D and E. Go right to D and E now.
Student gave this to me as soon as Top Hat was up.
Okay.
I just forgot to give it to you now.
Who's student? Oh, I have the record books for that. Yes.
Oh, it's my student.
What's that?
It's my student.
Okay, but no, I was just going to give it to the team. I have the Okay, let's do it. What time do you think the tub has the most water in it? At what time here between 0 and 7 minutes? It's all minutes, right? Between 0 and 7 minutes, what time do you think the tub has the most water in it? I heard 0. I heard around 4. 4.1. 0. Is the water in the tub level going down? This is a rate of change graph. Rate of change is what in the first 4.1 minutes? Positive. So rate of change is positive. Our quantity is going up, just like the sand graph, right? We had the whole time that the sand weight rate of change was positive, and all the time that the weight was going up, just like this in the first 4.1 seconds. Minutes. 4.1 minutes. Why? Because if the rate of change is positive, The quantity's going up. It's increasing. So that means it starts to decrease when the rate of change becomes negative. So it's maxed at 4.1. Does it make sense? Cool. What time does the water have the tubs have the least water in it? 0 to 7 minutes. 0 because the reduction from the, so what's happening? The clog is kind of loosening, right? And so it's draining faster and faster so that it kind of overtakes the rate of the water coming in. And so now we've got a negative overall rate. Water's flowing out of the tub. And so, but it doesn't go down as much clearly as how much it went up. So 0 minutes is when it's the least. We're going to skip C. Well, let's just say. So those are more or less the same question. More or less at t equals 7 than 0. More at times 7 than at times 0. More water. But the most water at 4.1 minutes. Okay, the a sub v t function. Did we get it? Where is Navit Kaur again? Did you get the a sub v function? Not yet. Okay. How about Rachel Erickson? Is Rachel here? Yeah. Did you come up with it? It's an exact accumulation function. It's going to be an... What's that? Didn't get it? So an exact accumulation function is an integral. The integral from what to what? 0 to t. So it's this. Our ending value of accumulation has to be our independent variable, t. Of what? So you could write either. You could write the function notation, or you can write the rule. I'll just go ahead and write the rule. And we talked about this, but we didn't explain it. You need a different variable. So I'm going to choose, you can't use t. You can't use the same variable. So I'm going to use u this time. Just needs to be anything different. We'll talk about it Thursday. Don't. So you could write the rule, or you can write function notation. I could have written r sub v u, r sub v of u. Does it make sense? To get the exact accumulation function is the integral from a, which is 0 in this case, to the current value of the independent variable of your rate function times the change, little change. Super important. Don't. Okay, we got one more question, please. Hold on, we got one more question. I want you to succeed on the test. That just takes another minute here. What about the function that gives the total volume? The total volume after the water was turned on. So notice, the 2.5 gallons initially does not come into the accumulation function. I told you that here, but it's not involved in the accumulation function, right? Because accumulation starts from 0, no matter how much was there before. So what's the volume function? 2.5 plus that. Or I could write this again. Doesn't matter, they're the same. Okay, we will have written quiz on Thursday, pertains to the exam.